and welcome to lecture 41. We are discussing about the design of low speed axial flow compressor. In last sessions we were discussing about the design of low speed axial flow compressor using two different approaches. First, that's what is by using say free vortex concept, and we started talking about the fundamental approach. So for fundamental approach, we are taking our mid station calculation, that's what is similar to what all we have done for free vortex concept, by considering our total pressure rise to be 500 at the mid station. And based on that, we have done our fundamental calculation of different velocity components, different flow angles, degree of reaction, diffusion factor, de-Holler's factor. We also have calculated different flow angles, say incidence angle, deviation angle, camber angle, stagger angle. So at mid station, all these numbers, they are known to us now. Now, as we have discussed during our class session, in order to use this fundamental approach, we are having three different possibilities. Like we can go with say hub loaded design configuration, we can go with mid loaded configuration, and we can go with say tip loaded configuration. So here if you look at, these are the different approaches what we have discussed. Now in order to go for say design approach, say at mid station we have done our calculation for all flow angles, all velocity components, everything. Now what all we have used is we have compared our aerodynamic work and thermodynamic work, and based on that we have calculated what will be our exit wall component. Similarly, here in this case, what we will be doing at hub, we will be taking say our pressure rise, expected total pressure rise to be 800 Pascal and 1200 Pascal. And for that we have discussed the approaches. So here this is what is based on what all assumptions we have done. Say at mid station we are having say total pressure rise of 1000 Pascal. At hub station we have assumed that to be 800 Pascal, and near tip we have assumed that to be 1200 Pascal. And then as we have discussed, we need to look at the parameters and their variation. So what observation we found is delta beta near the hub, that's what is coming to be slightly on a larger, or say it is more than 45 degree. So that's where we feel we need to have some control, or we need to do some modification. If you look at say degree of reaction, that's what is say coming to be lower, it's 0.32. At the hub we are having our relative velocity ratio, it is 0.85, it's little high on that side. We have our diffusion factor to be 0.31. Now as we have discussed all designs what we will be doing for axial flow compressor, let it be low speed compressor or let it be high speed compressor, we will be using our fundamental approach using say axial seat design. Here as we have discussed, we will be having all flexibility to do modification, and immediately we will be having cross check or say variation in number visually. If we are doing coding for making the design program, that is also one of the possibility, but there we will be having number of seats that will be generated. That's what ultimately you need to check with. So it's better we will be doing this using the say axial seat program. Now here in this case, say what rotor we are designing, we will be providing some clearance between casing and my rotor tip. When we are providing that clearance, we learn that's what will be subjected to some losses, and those losses we have defined as a tip clearance loss, and that's what is a major contributor in sense of total pressure loss or pressurizing capacity of my stage. So in order to take care of that, what we will be doing, in place of designing for say 1000 Pascal, let's try of putting that on slightly on higher side, say maybe say 1080 Pascal. And in order to do that, we have modified our delta P0 at hub to be 699. At mid station also we have modified now, in spite of say 1000 we will be taking 1070, and at the tip we will be taking 1500 Pascal. So in overall, if we look at, we are getting our total pressure rise, that's what is coming 1080 Pascal. Okay. Now when we are doing this modification, what will happen? That's what is giving me my delta beta, that's what will be reduced from 48 to 41. So this is what is the flexibility what we have by using this Excel sheet program. Okay. At the same time, we can see our degree of reaction, that's what has increased to 0.40, and relative velocity, that's what has reduced slightly, say to 0.83, and diffusion factor, we can say it is 0.309. As we have discussed, here we can do modification in sense of say number of blades also, since we are maintaining our uniformity for all the three design approaches, so that we will be having one-to-one comparison. That's why we are not changing. But you can understand, suppose if I am looking for say my diffusion factor to be in the range of 0.6, accordingly I will be changing my number of blades. Okay, because we know diffusion factor, that's what is a function of my solidity, and solidity we are defining as a chord to pitch. So with change of my number of blade or by changing my chord, we are able to modify our solidity, and that's what will be reflecting in sense of change of diffusion factor. So with this, let's try to divide this into different 11 stations what we have done. So here if you look at, we have divided that into equal number of stations, as we have discussed, say it is in the interval of 0.01 meter. And again I am telling you, suppose say if you are looking for say more accurate or more precise design, that time you need to go with more number of stations. Suppose say this is what is low aspect ratio blade, so you can say my height of the blade is say smaller. It may be possible that you will be having taller blades. For taller blades, you increase your number of stations. So variation of my blade geometry, that's what will be taken care more precisely in that case. Okay. Now here, unlike what we have done for our say free vortex concept, where everything that's what was depending on my constant and radius. So radius, that's what was remaining constant, and that's the reason why what all we are getting, that's what we were accepting. Now here in this case, what we have flexibility, if we look at this delta P0, I can vary in sense of numbers. Now what all we need to check is how my angles are changing. Listen me carefully here. So here if you look at, just keep on eye here. Say you are putting this number at hub, so you will be getting your delta beta. Okay. Now say next I will be putting in sense such that I will be having say some particular trend for variation of beta 2 or say delta beta. Since my beta 1, that's what is a function of Ca by U, that's why we are not finding much change there. Here this is what is in our control. And that's the reason why we need to be very careful in sense of selecting this number. Do not get confused. This is what is based on number of iterations, number of trials. Okay. Maybe you can put one plot here where you can put say change of your radius. Along with that, you just put what will be your delta beta, or maybe you can put one of the observed parameters, say degree of reaction, or maybe you can put say one parameter, say diffusion factor. It's your choice, but that need to have particular trend. Okay. Suppose say if we will be having these numbers coming to be zigzag, say here at hub, suppose I have taken 699, immediate station I can take 800 also, but we need to understand when I am doing my averaging, that should come what we are expecting. Okay. At the same time, what numbers you are putting near the tip region, that's what you need to keep on eye with your diffusion factor. Okay. Suppose say if I am changing this number, that's what will be changing my diffusion factor. So you can have two observations. You need to have two observations. First, that's what is near the hub region, and second, that's what is near the tip region. Now suppose say when you are doing your iterations by putting different numbers, it may possible that near a mid station you will be having some kind of say droop, or maybe it will be having upside kind of train. So just adjust that number. It is designer's choice, it's your choice, you need to decide with that number. Okay, so that's how these numbers they are being selected with. Now since we have arranged it in a systematic way, you can see we are having this delta beta, that's what is having particular trend. Okay, same way here diffusion factor also you will be finding a particular trend. We are having say keep on eye for say degree of reaction, that's what is varying from 0.4 to 0.68. Even at the same time our de Holler's factor, that's what is varying from 0.83 to 0.65. So near the tip region this de Holler's number, that's what is having say slightly on a lower side, but that's what is accepted in the sense. Okay, it is preferred that you will be going with this number to be slightly higher, but by doing that maybe you need to play with the other numbers and you need to keep on eye. So whole this seat or whole design, that's what is being based on what number we are selecting for this delta P0. Okay, now this is what is a very great flexibility to the designer. Okay, now once we are putting all this together, that's what is giving me my variation of delta beta. So here if you look at, this is what is say my beta 1 angle, and if you compare to our free vortex, here my delta beta at hub, that's what is slightly lower, and at the tip that's what has increased in the train. Again say what delta P0 what you are selecting at different station, based on that the delta beta, that's what is in your control. You can adjust your delta beta, you can put as per your expectation, as per your requirement. Okay, if you are looking for say highly twisted blade, you are looking for low twisted blade, accordingly we need to check with. Okay, now here in this case this is what is representing my diffusion factor, and as we have discussed, that's what is showing me higher diffusion factor near the tip region and comparatively low compared to your tip, that's what is say on lower side, that's what is at the hub. Now this is what is representing how my velocity components, loading coefficient and flow coefficient, that's what is varying, and this is what is at say degree of reaction. You can see my degree of reaction, that's what is varying from 0.4 to 0.68. Okay, now this is what will give idea about the selection of this number. So when you are making your Excel sheet program, that time maybe you can put this kind of plot side by, so that you will understand what is a trend, what you are looking for, is it coming or not. Okay, now based on that our next step, that's what will be to design say our stator. And for stator what we have learned, for say stage configuration rotor stator combination, we are assuming our absolute velocity coming out from the rotor, that's what will be equal to say our velocity, absolute velocity at the entry of my stator. So we can say what is my alpha 2 coming out from the rotor, that's what will be the entry for my stator. That's the reason we are putting here this alpha 3m, that's what is 0, that's what is at the exit, and alpha 2m, that's what is 39.69. Remember we have modified our mid station, and that's the reason why we need to put this set. Say for earlier calculation for free vortex, there we have taken at mid station the pressure was 1000 Pascal, and here this is what is 1070 Pascal, and that's the reason why we are having our alpha or delta alpha, that's what will be different at the mid station. So you need to be little careful in sense of doing the calculation. So once we are calculating this delta alpha, that's what is coming 39.69. Now our next target, that's what is to calculate what is our diffusion factor, and that's what we are calculating based on my pitch and chord. We are basically calculating our solidity. So here my pitch, that's what is given by, this is what we are calculating at the mid station. So we will be taking carefully diameter at the mid station, and number of blades here we have taken as a 17. Okay, So that's what will be giving me my pitch to be 0.055 meter. Okay. Now based on our available chord, that's what is say 0.1 meter, we can calculate what will be our solidity at the mid station, and we can calculate what will be the diffusion factor for the stator. Again, this is to remind what angles we are putting. For rotor we are taking basically relative flow angles, here we need to take absolute flow angles. That's what is the change in the formulation. Okay. If we are calculating our diffusion factor for the stator, that's what is coming 0.40. Okay. And degree of reaction, as we have discussed, that's what we can say, it is 1 minus degree of reaction of my rotor. So that's what is giving me my say degree of reaction to be 0.4. Okay. Now we need to check with the angles. That's what say what is my say camber angle, what will be my deviation angle, what will be my stagger angle. So those we are calculating based on Carter's parameter or M factor. So here in this case, this M factor, that's what is coming 0.327. We can calculate what will be our camber angle, that's what will be delta alpha. In the case of my rotor, we are taking delta beta, and this is what is my incidence angle. Let me tell you, at mid station for stator, we are assuming our incidence angle to be 0. Okay, so this is what is say 30, and if you will be putting this, this is what will be giving me my delta say deviation angle. Okay, we can calculate our camber angle, we can calculate our deviation angle, and based on this formulation we can calculate what will be our stagger angle. Okay. Now, so once we are having all these numbers, that's what is coming with us, we can check with what all will be the changes. Okay. So here we are putting our observed parameter as a diffusion factor. So you can say this is what is 0.34, and at the tip that's what is coming 0.48. So you can say near the tip region your stator is highly loaded in that sense. Okay. And other parameters we can say our degree of reaction, that's what we are calculating based on say 1 minus degree of reaction of your rotor. So you can say my degree of reaction at hub, that's what is coming to be larger. Okay. And let's see what all changes we are finding in sense when we are incorporating the calculation of the stator. So here in this case, if you look at my stator, that's what is having say diffusion factor to be slightly on the higher side near the hub region, and near the tip region that's what is say decreasing. Okay. Same way here, this degree of reaction train, that's what we have already compared with. Okay. So this is what is 1 minus degree of reaction of my rotor. Now this is what is giving us the idea about the calculation of all flow angles, and based on that what all we have done, say we can assume our aerofoil to be C4. We are having now understanding of calculating x and y coordinate for the aerofoil for upper surface as well as for the lower surface. Since we are using C4 aerofoil, that's the reason we know the CG point, we know what is our stagger angle, and based on that we can do the calculation here. Okay, and we can generate our geometry. Now interestingly here, if you look at this blade, rotor blade, that's what is having slightly lower twist compared to what all we have done for free vortex design. Okay, same way for stator also, this is what is a variation of my angles. Let's try to compare one by one. Suppose say here if you look at, there are two plots. Say if you look at this golden color, that's what is representing my fundamental approach, and this silver color, that's what is representing my say free vortex concept. So for free vortex, as we have discussed, my delta beta, that's what is coming to be larger near the hub region. At the same time, if you find near the tip also that angle, that's what is coming to be slightly on higher side. So that's what is giving say highly twisted blade. You can see this high twist from pressure side. Same way we can look at say twist from the suction side. So this is what is representing my fundamental approach, and say other one, that's what is representing my free vortex concept. So that's why, so this is what is a designer's choice to opt for which kind of design method he or she will be opting for. Similarly here, if you look at my angles for stator also, they are going to change. Remember, for both the configuration, our exit, that's what we are assuming to be axial one. Okay, so this is what is giving us idea about how my blade geometries that will be changing. Now let's try to compare what all we have seen from these two methods. So here, if you are comparing, we are having free vortex method, we have our fundamental method, and as we have discussed, say this beta 1, that's what will be same for both the methods. My beta 2, we can see here, say here in this case, when we are looking at beta 2 using our fundamental approach, my angle beta 2, my exit angle, that's what is coming to be slightly lower. That's what is giving me my delta beta to be lower near the hub region. Okay, in line to that, if we are looking at near the tip region, that delta beta for say fundamental method, it is coming on higher side. Basically that's what is representing our blade twist, it's less, and that's what we have seen even in our 3D geometry for rotor blades. Okay, now here in this case, if you are comparing, this is what is representing my diffusion factor. So for free vortex concept, if you observe carefully, suppose say when we are talking about say rotor, so my rotor, that's what is having say diffusion factor, that's what was lower near the hub, and that's what is higher on mid section, and that's what is lower near the tip region. Okay, so just understand, we say our diffusion factor, that is nothing but that's what is representing my aerodynamic diffusion. Okay, now if we take carefully, say for stator, if we are observing, we will be having our diffusion factor to be larger near the hub region. Just understand one thing, this delta beta what we are considering to be large for the rotor, that's what is reflecting here. Your stator need to do more amount of work near the hub region because you are having great turning near the hub region for the rotor. Okay, and that's the reason why this is what is say you are having diffusion factor to be larger near the tip region, that's what is coming to be lower. Now for the case of say our fundamental approach, we can understand that's what we have designed for tip loaded, it is reflecting here. What it says, my say diffusion factor for both rotor and stator, that's what is coming to be higher near the tip region. Okay, so this is what is one of the important observed parameter, like what is happening with your say delta beta, what is happening with your diffusion factor. Now let's see, suppose if we are considering what is happening with our say phi and psi. So we can say the value of our phi, that's what is not changing at this moment because my CA value and my U value, that's what is same. But at the same time, when we are looking at say our loading coefficient, we can see for our fundamental approach, this is what is representing say systematic loading throughout my span. Okay, and if we observe here, say for free vortex kind of configuration, my loading, that's what is changing all the way from hub to tip. Okay, and in line to that, if you are looking at, this is what is representing my degree of reaction, and as we have discussed, degree of reaction, that's what is representing your thermodynamic diffusion. So in line to what all we have discussed about the diffusion factor, similar kind of trend, that's what we are observing here. And here if you look at my degree of reaction, if we are talking about the stator, that's what is coming to be larger. Okay, because your work that need to be done by stator, that's what is on higher side. Okay. Now similar trend, if we are comparing with both the methods, we are having good control in sense of my degree of reaction. We can say it is more in sense of tip loaded, that's what is been reflected here in sense of variation. Okay. Now this is what is representing our parameter, we call say our de-Holler's factor. So this de-Holler factor we are comparing for say free vortex, that's what is very high near my hub region, and that's what is going to change near the tip region. And if we are comparing here with say our fundamental approach, that's what is saying my de-Holler's number, that's what is decreasing, but decrease, that's what is in a systematic way. Okay. Same way we will be having say our variation of absolute velocity component, basically that's what is representing my flow acceleration. Okay. So here if you look at my C3 by C2, that's what is coming nearly constant kind of thing, but for say free vortex concept we can say we are having more acceleration of our flow, that's what is happening, that's what is near the tip region. Okay. Now this is what all we have discussed in sense of say comparison for free vortex concept, as well as we have discussed about say our fundamental method. And what we realize is say free vortex concept, that's what is easy in sense of doing our calculation, but that has many constraints. Positive thing about the free vortex concept is it is satisfying our radial equilibrium equation, and that's what is our need. But at the same time, when we are looking at say our blade twist near the hub region, that's what is coming to be larger. For this design, our degree of reaction near the hub region, that's what was coming reasonably good, but in many designs where you are having say hub diameter to be smaller, there may be possibility that degree of reaction will go negative. So that care we need to take care of. And in order to avoid such kind of situation, and in order to have great control in sense of our operation, fundamental approach, that's what is giving more systematic way of designing. We have more control in sense of what we are expecting throughout our span. One more thing is, more the number of stations we will be selecting, more smoother will be our curvature. At the same time, when we are making our aerofoil, as we have discussed, we need to select more number of points, very close points, maybe in sense of thousands, so that the curvature when we are making by joining these points, that's what will be giving say continuous curve and without any zigzag. Okay. So I'm sure you people may be making your design Excel sheet for solving this numerical. I prefer you do practice, you are having